Welcome everyone. Today we will see when a vehicle is standing still, its weight is shared between the front and rear axles. This is static load distribution, set only by mass, wheelbase, and center of gravity position. The moment the vehicle accelerates, brakes, or corners, inertia shifts this weight between axles sides. This is dynamic load transfer. No mass moves, only forces redistribute. This transfer changes tire grip, traction limits, braking capacity, and stability, making load transfer the foundation for vehicle performance, safety, and control, especially critical for high-torque electric vehicles. Axle loads can also be solved by taking moments about the center of gravity. For a moment balance, the rear axle force times distance B equals the front axle force times distance A. This gives the relation FZR 0 times B equals FZF 0 times A. Vertical force balance gives FZF0 plus FCR0 equals mg. Substituting to eliminate the front axle force leads to FZR0 times A plus B equals mg times A. Since the wheelbase L equals A plus B, the final result is FZR0 equals mg times A divided by L. Static axle loads depend only on the vehicle mass and the location of the center of gravity. For a vehicle with wheelbase L equals A plus B, the front axle load is FCF0 equals B divided by L times mg. The rear axle load is FCR0 equals A divided by L times mg. These equations show that the center of gravity position alone determines how weight is distributed when the vehicle is stationary. This static load split is the reference point for all dynamic load transfer calculations. D'Alembert's principle allows a dynamic problem to be treated as a static one. An accelerating body can be analyzed by adding an inertial force, given by Fi equals ma, applied at the center of mass and acting opposite to the acceleration. This single fictitious force converts a motion problem into a static equilibrium problem. A pitching moment is the torque that rotates the vehicle about its left-right axis. This moment exists because the inertial force acts at a height h above the ground, while tire forces act at ground level, creating a vertical moment arm. During acceleration or braking, the normal loads on the axles change due to load transfer. The amount of longitudinal load transfer is given by delta Fz equals mAh divided by L. Here, A is the longitudinal acceleration, h is the center of gravity height, and L is the wheelbase. When the vehicle accelerates, load shifts from the front axle to the rear axle. When the vehicle brakes, load shifts from the rear axle to the front axle. During acceleration, this causes the front of the vehicle to nose up. During braking, it causes the front of the vehicle to nose down. Load transfer increases when the center of gravity is higher or the wheelbase is shorter. For the same acceleration, a taller CG produces a larger load shift. A shorter wheelbase also amplifies the load transfer. Increasing the magnitude of acceleration further increases this effect. These changes are caused purely by moments acting on the vehicle. They are not due to mass moving inside the vehicle and occur even if the vehicle is perfectly rigid. When there is no vertical acceleration, the total normal force on the vehicle equals its weight. This gives the relation FCF plus FCR equals mg. During acceleration, an inertial force acts at the center of gravity and creates a pitching moment. This inertial moment is mi equals m times a x times h. Taking moments about the center of gravity and using the wheelbase distances a and b gives the equilibrium equation FCR times b minus FCF times a minus m times ax times h equals 0. These two equations together allow the front and rear axle loads to be determined during acceleration. The front axle force can be written as FZF equals mg minus FCR. Substituting this into the moment equation and using the wheelbase L equals A plus B leads to the final expression for the rear axle load. The dynamic rear normal force is FCR equals mga plus m times ax times h divided by L. This equation clearly shows how the rear axle load depends on vehicle geometry and longitudinal acceleration. Rearranging the expression separates the rear axle load into two parts. The first part is the static rear load, FZR0 equals mga divided by L. The second part is the load transfer due to acceleration, delta F equals m times ax times h divided by L. This shows exactly how much weight is transferred to the rear axle when the throttle is applied. Force equilibrium requires that the total vehicle weight remains constant. The front axle load can be written as its static value minus the load transfer. The static front load is FZF0 equals mgb divided by L. Subtracting the transfer gives the dynamic front load. This confirms that whatever load the rear axle gains, the front axle loses by the same amount. Axle loads can be written in a compact and practical form. The rear axle load is FZR equals FZR0 plus delta F. The front axle load is FZF equals FCF0 minus delta F. The load transfer term is given by delta F equals M times AX times H divided by L. These formulas allow engineers to predict axle loads for any acceleration or braking condition. They are used to design suspension systems, manage traction, and maintain vehicle balance during longitudinal maneuvers. A positive longitudinal acceleration shifts load toward the rear axle. A negative longitudinal acceleration during braking shifts load toward the front axle. This continuous load transfer changes how much grip each tire can generate. As a result, acceleration and braking directly affect vehicle stability and control in real time. Traction comes from friction between the tire and the road. When engine or brake torque is applied to a wheel, the tire pushes on the road. The road responds with a friction force that moves the vehicle forward or slows it down. This friction force is responsible for every acceleration and every controlled stop. Friction also has a maximum limit. If the required force exceeds this limit, the tire can no longer grip the road. The tire then slips, either spinning during acceleration or locking during braking. Understanding this friction limit is essential for vehicle control and safety. Coulomb's law defines the maximum friction force that can exist between two surfaces. It states that the tangential friction force cannot exceed the product of the friction coefficient and the normal load. At the point of impending slip, this becomes F friction max equals mu times Fn. This simple rule sets the fundamental limit on how much force friction can provide. The same law applies directly to tires. For a tire, the normal load is Fz and the traction force is Ft. At the limit of grip, the relation becomes Ft max equals mu times Fz. This equation is a direct application of classical friction theory to tire-road interaction. The maximum traction of an axle comes from the combined grip of its tires. For a driven axle with two tires, the total available traction is the sum of their limits, Ft max axle equal to mu Fc1 plus Fc2 equal to mu Fc axle. Because the friction coefficient mu is the same for both tires, axle traction depends directly on the total vertical load carried by that axle. Increasing vertical load on the driven wheels increases available traction. This is why weight transfer during acceleration or braking strongly affects performance. On low-mu surfaces like ice, the traction limit shrinks dramatically, requiring smoother inputs. All-wheel drive helps by spreading load and traction demand across more tires. Friction should be treated as a usable resource, not a barrier. Maximum performance comes from operating just below the traction limit, where grip is fully used without slipping. The same equation guides both engineering and driving decisions. Ft max equal to mu Fc. Engineers design vehicles around it, and drivers instinctively respect it through throttle and brake control. Let us look into the relation between dynamic load transfer and the road grip. When an electric vehicle accelerates, brakes, or turns, inertia causes the vehicle's weight to shift front to rear or side to side. During acceleration, weight moves rearward. During braking, weight moves forward. During cornering, weight shifts outward toward the outside wheels. The total vehicle mass does not change. Only the vertical load on each tire changes. This load shift is quantified by the relation delta Fz equals mass times acceleration times center of gravity height divided by wheelbase. As vertical load moves, tire grip is redistributed instantly. The tires carrying more load can generate more force, which directly limits how much motor torque or braking force can be applied. In short, weight transfer controls grip, and grip controls vehicle performance and stability. Electric motors can deliver maximum torque even at zero speed. However, the tires can turn this torque into forward motion only if enough vertical load is present. If too much torque is applied to a lightly loaded wheel, the tire reaches its friction limit and spins. This wastes energy and actually slows the vehicle launch. The usable traction at any wheel is limited by the friction rule, spoken as maximum traction force equals friction coefficient times vertical load. Static axle load tells us how much grip is available at rest. Dynamic load transfer tells us how grip changes during acceleration. By combining static bias and dynamic shift, engineers know exactly how much throttle can be applied before tire slip begins. The lesson is clear: instant torque is powerful, but traction decides how much of it can be used. Engineers carefully place the heavy battery pack and choose between single motor or dual motor layouts to control how weight sits on the vehicle at rest and how it shifts during acceleration. A rear bias battery layout increases rear axle load, giving more grip to the driven wheels and improving rear-wheel drive launches. With dual motor all-wheel drive, torque can be split between front and rear axles. As acceleration shifts weight rearward, more torque is sent to the axle that gains load. This allows the vehicle to use more of the instant electric power without wheel slip, turning battery placement and drivetrain choice into powerful tools for traction and performance optimization. Consider a 1,600 kilogram electric vehicle with a 2.8 meter wheelbase and a 0.55 meter center of gravity height. The total static weight is 15,696 newtons, split evenly into 7,848 newtons at the front axle and the rear axle. On a road with friction coefficient mu equals 1, each axle can generate 7,848 newtons of longitudinal force before slipping. For a rear-wheel drive version, this rear axle limit defines the initial traction ceiling at launch. Now let us accelerate at 0.5 g, which is 4.905 meters per second squared. This acceleration transfers 1,541 newtons of load from the front axle to the rear axle. The new axle loads become 6,307 newtons at the front and 9,389 newtons at the rear. Because traction equals mu times vertical load, the rear tires can now generate 9,389 newtons of drive force. That is 1,541 newtons more propulsion, created purely by weight transfer, raising usable motor torque without changing tires, rubber, or road grip. With the higher rear load, the EV can use 9,389 newtons of drive force, about 19% more than at rest. Any torque beyond 9,389 newtons causes wheel spin, so traction control must limit demand there. This shows that dynamic load transfer creates real, usable grip, not just a theoretical idea. Static weight distribution sets your starting grip balance at each axle. The moment you accelerate, dynamic load transfer adds extra grip to the driven wheels. If this added grip is managed wisely, using motor torque control, battery placement, and suspension geometry, the EV converts instant electric torque into forward motion. If not, the excess becomes wheel spin, noise, and wasted energy. We start from static equilibrium on a wheelbase L, with the center of gravity located A from the front axle and B from the rear. When the vehicle accelerates, with longitudinal acceleration AX and inertial force M times AX acts at the CG height H, creating a pitching moment. Dividing this moment by the wheelbase gives the load transfer delta Fz equals M times AX times H over L. This load is removed from the front axle and added to the rear axle. The result directly limits usable motor torque because available traction depends on normal load. The normal forces at the tires, both static and dynamic, set the absolute limits for traction, braking, torque delivery, and overall energy efficiency. In electric vehicles, where motor torque is available instantly, predicting these forces is essential for safety, performance, and control. The approach begins from first principles. Static weight distribution is derived using basic force and moment equilibrium. Then, longitudinal acceleration and braking introduce inertia forces that redistribute this load between the axles. Each step directly connects vehicle geometry and acceleration to traction limits and usable motor torque, forming a clear physical path from fundamental mechanics to real-world EV performance. The traction force a vehicle can generate is always limited by friction. When the dynamically changing normal load Fz is substituted into the inequality Ft less than or equal to mu times Fz, the acceleration itself becomes bounded. Solving this relation for a rear-wheel drive vehicle produces a clear physical limit, Ax less than or equal to mug divided by L, mu times h. This expression reveals a hard ceiling on acceleration that no motor or controller can exceed. It shows how friction coefficient mu, gravity g, vehicle geometry A and L, and center of gravity height h together determine the maximum achievable acceleration. No matter how powerful the drivetrain, this limit is enforced purely by physics. Using this traction-limited acceleration formula, we substitute real vehicle values. The vehicle mass is 1,900 kilograms. The wheelbase is 2.9 meters. The distance from the center of gravity to the front axle is 1.2 meters. The center of gravity height is 0.52 meters. The road friction coefficient is 0.9. When these values are placed into the acceleration limit equation, the maximum achievable longitudinal acceleration is 5.15 meters per second squared. This means the driven wheels reach their traction limit at this acceleration. Beyond this point, adding more motor torque will only cause wheel slip, not faster launch. The result proves that first principle physics directly sets real-world vehicle acceleration performance. Consider a 1,500 kilogram car braking at 6 meters per second squared. The wheelbase is 2.6 meters, CG height is 0.55 meters, with A equal to 1.1 meters and B equal to 1.5 meters. Using delta Fz equals max h over L, the braking load transfer is 1903 newtons. This increases the front axle load to 10,384 newtons and reduces the rear axle load to 4,310 newtons. Even moderate braking shifts nearly 2 kilonewtons forward, strongly influencing ABS behavior and brake proportioning. We now substitute sample vehicle data into the full lateral dynamics equations. The front cornering stiffness CF is 80 kilonewtons per radian, and the rear cornering stiffness CR is 100 kilonewtons per radian. The center of gravity is 1.2 meters from the front axle and 1.6 meters from the rear axle. The forward speed U is 20 meters per second. The lateral velocity phi is 0.5 meters per second. The yaw rate R is 0.1 radians per second, and the steering angle delta is 5 degrees. Substituting these values into the equations gives the front lateral tire force FYF equals 4,480 newtons. The rear lateral tire force FYR equals minus 1,700 newtons. And the yaw acceleration R dot equals 3.24 radians per second squared. These results show a strong front response and a controlled rear reaction, predicting quick turn-in with stable understeer behavior. The positive yaw acceleration of 3.24 radians per second squared indicates a strong and responsive steering reaction. The balance between the front and rear lateral tire forces determines whether the vehicle tends toward understeer or oversteer. When front forces dominate, the vehicle remains stable and understeers. When rear forces dominate, the vehicle becomes more agile and can oversteer. This example shows that a clear understanding of earth frame equations of motion allows engineers to deliberately tune suspension, tires, and control systems to achieve safe, predictable, and well-balanced vehicle handling. Consider an electric vehicle with a mass of 1,900 kilograms. The wheelbase L is 2.9 meters, and the distance from the center of gravity to the rear axle A is 1.2 meters. Using the static load formulas, the rear axle static load FZR0 equals 7,713 newtons, and the front axle static load FZF0 equals 10,925 newtons. These values define the baseline traction available at each axle before acceleration, braking, or cornering begins. Now consider the vehicle accelerating at 4 meters per second squared with a center of gravity height of 0.52 meters. Using delta Fz equals max h over L, the load transfer is 1,363 newtons. This increases the rear axle load to 9,076 newtons and reduces the front axle load to 9,562 newtons. This result shows how acceleration instantly reallocates tire grip, directly shaping traction and vehicle response in real time. Using a friction coefficient of 0.9, we substitute mu equals 0.9 into the closed form acceleration limit. the maximum achievable longitudinal acceleration becomes AX, maximum equals 5.15 meters per second squared. This result proves that tire road friction and vehicle geometry, not peak motor torque, set the ultimate launch performance of the car. Now observe the effect of center of gravity height. When the CG height is reduced from 0.52 meters to 0.35 meters, the maximum achievable acceleration increases to 5.45 meters per second squared. This shows that lowering the battery and mass in the vehicle directly increases available traction, expands the acceleration envelope, and helps reduce lap times. Static axle loads define the starting traction level. Dynamic load transfer sets the upper acceleration and braking limits. Together they form a fixed, immutable operating corridor within which every electric vehicle must size its motors, brakes, and control algorithms. These limits are set by physics and geometry, not software or peak power. Let's try to understand the engineering action list for designing a traction controller. First, place the battery to tune the static front-rear load split. Next, lower the center of gravity to reduce load transfer during acceleration and braking. Then, calibrate motor torque maps, so they never exceed the calculated maximum acceleration AX max. Finally, embed these equations directly into traction control lookup tables to deliver maximum grip with optimal energy efficiency. Today, we learned that static axle loads set the baseline weight carried by the front and rear tires when the vehicle is at rest. This baseline depends only on vehicle mass, wheelbase, and CG location. We then saw how dynamic load transfer occurs during acceleration and braking. Longitudinal acceleration creates an inertial force at the CG height, which shifts load between axles by the amount delta equal to m times a times h divided by L. This load transfer does not move mass, it redistributes tire grip. What the front axle loses, the rear axle gains, and vice versa. Finally, we connected load transfer to real engineering decisions. Axle loads directly limit traction, braking, ABS behavior, and motor torque usage. The key takeaway is simple. You cannot design power, brakes, or control systems without understanding axle load transfer, because physics, not software, sets the ultimate limits. See you on another topic in EV powertrains in the next video.